Okay, now I'm going to move on to section 6A.2, which talks about equilibria of various kinds. The first one we're going to look at is the equilibrium between perfect gases. So we're still doing this basic reaction here where we have species A and species B are in equilibrium with each other. In this case, though, A and B are gases. So way back in chapter 3, section E, for perfect gases, we had this formula for the chemical potential. And you can find the derivation and discussion of this equation on page 58 of my lecture notes. It's mentioned again on page 80 as well. So as we just saw, Gibbs energy of reaction is the difference in the chemical potentials of A and B. And now I'm going to substitute this equation in for each of these, mu A and mu B. Okay, where this is the equation for mu B, and this is the equation for mu A. Now I'm going to group the terms. You can see that I can group the mu B minus mu A terms together, and that looks a lot like this, but at standard state. So we're going to call this delta RG standard state. P standard is, in the cases that we're going to be using it, it'll probably typically just be 1 bar. But they're going to cancel in this case because here I have the difference between two natural logs. So I'm going to take the ratio of their arguments and combine them into a single natural log. So I'm going to end up with a natural log of PB over P standard divided by PA over P standard. So the P standards will cancel, and I'm left with RT ln PB over PA, the ratio of the partial pressures of the two gases. So this quantity right here, PB over PA, we're going to call this Q. And we're going to name it the reaction quotient. So in a minute, we'll get into a definition of Q that's more general. But for now, we're going to use PB over PA. So what is the range of Q? Well, at the smallest, it can be 0, which is when PB is 0. So that means that we're talking about pure A. PB has no partial pressure. It's not present. So all we have is gas A. 2 ranges from 0 to infinity, which would be the case when PA is 0, which means that we're talking about pure B, gas B only. All right, so I can rewrite this previous equation with Q inside the natural log, and I end up with this. And I'm going to call this equation star because we're going to be using it again. So here we defined this standard reaction Gibbs energy as mu B minus mu A standard. So I'm going to write that again, but I'm also going to point out that in practice, we've done this before. This quantity, the standard Gibbs energy of reaction, can be computed from the sum over all of the products and reactants of the Gibbs energy of formation of each product and reactant with this stoichiometric coefficient in front. So in this case where we just have A and B in equilibrium, we only have 2 species in our sum. So we have two terms in our sum. Vj for B is positive 1. So it's going to be the delta F, the Gibbs energy of formation of B. minus the Gibbs energy of formation of A. And these are both for gases, for the gas state. Okay, as we covered previously, at equilibrium, delta Rg is equal to 0. And we covered that in 6A.1. And if I take this and I put it into my equation star here, it would be the left-hand side. It becomes 0. So we sub this into star, and we get 0 equals. And remember, Q is the ratio of the partial pressures. Q is going to change as the reaction progresses. And so if we're talking about the equilibrium point of this reaction, we're going to give Q a special name. So Q at equilibrium which is the ratio of the partial pressures at equilibrium, we're going to call that quantity K. So K is the equilibrium value of Q. And we're going to get a more general definition of K here in just a minute. So K is an example of what's called an equilibrium constant. And now I'm going to solve this equation here for K, where remember Q, since we're talking about equilibrium here, Q is equal to K. So this is an intermediate step in solving for K. I let Q be K, and then I've subtracted this over. But this equation is used a lot, and we're going to use it here in a minute. So even though it's an intermediate step, I just wanted to pause there and put a box around it. But from here, we can still solve for K. And it's going to be E to the negative delta Rg over Rt. All right, so let's do an example where we have just these two species in equilibrium with each other, and they're both gases. One example that you'll find in your textbook is the isomerization of pentane to 2-methylbutane. These two are isomers of each other. So I'm going to write out the equation for this process here. Okay, and so pentane and 2-methylbutane, if you count up the C's and H's, you'll see that these are isomers. And we're given some data here that the standard Gibbs energy of this reaction is negative 6.7 kilojoules per mole at a temperature of 298 Kelvin. And so now with that information, we can use the previous equation to solve for K, because we now know delta Rg, we know T, and we know R. So K equals E to the delta Rg, the negative of that, so the negative sign cancels here. I converted this to joules from kilojoules because the gas constant is in joules as well, at least the one that I have memorized is. And notice here that joules per mole and joules per mole are in the numerator and denominator, so they cancel. And then down here in the denominator, I've got Kelvin and 1 over Kelvin, so those cancel. So this ends up being a unitless number, and this is something that we're going to see again about K. K is a dimensionless number. And when you plug all these numbers into a calculator, you get 14.9, no units. So that is the equilibrium constant of this reaction. And as we'll see in a minute, what can you do with this? Well, one thing that you can do here is you can use this equilibrium constant to determine how much of each of these gases will be present in the equilibrium state. Okay, so you can find the ratio of these two in the equilibrium state using K. And so we'll see an example, not the same example, but a similar example of that. So as an important note, I just want to add that a reaction is spontaneous if the Gibbs energy of reaction is negative, as we've discussed before. but that's not necessarily true if the standard Gibbs energy of reaction is less than 0. Okay, so this is our spontaneity condition here, not this, but this quantity is still useful because we can use it to find K. Okay, so to change gears just a little bit, I want to talk about how a chemical equation can be written in a very compact form using the stoichiometric coefficients. And it looks like this. 0 equals the sum over all of the products and reactants of the stoichiometric number, Vj, times species J. That's a chemical equation. So let me give you an example. This is a general and compact form for writing a chemical equation. So let's say we have 4 species, A, B, C, and D, and we have the stoichiometric numbers. For A is -2, for B is -1, for C is 3, and for D is 1. So let's just plug those in here and see what we get. So left-hand side is 0. The right-hand side is going to be the sum of each of these times the symbol of the species that they are representing, the stoichiometric number for. So I have -2 times A, right? Because that's new A times A, plus new B, so that's -1 times B, plus new C, which is 3 times C, plus 1 times D. And rearranging this a little bit, we get 2A plus B on one side, and we get 3C plus D on the other side, where I've changed the equal sign into a reaction symbol. Okay, so that was kind of an aside on this compact notation that can be used to write a chemical equation. Now I want to talk about something that we first saw in section 5A, which is this formula for dg, a infinitesimal change in the Gibbs free energy. And we're holding P and T constant. We're going to write this as the sum of the chemical potential for each species times the change in the number of moles of each species. Okay, so you can see that in my notes on page 76. Okay, and then earlier we were able to define or write a relationship between this, dN, and the reaction extent, dC. Right, so I'm gonna bring that formula into this. So that formula, which is from page 111 of the notes just a few pages ago, is this. And so I'm going to take this and I'm going to put it up here to get a formula for dg. And so I get the sum of mu j, nu j, dc. And notice that dc is the same in every single term. So I'm going to factor that one out. So now I have dc times this sum. And now I'm going to rearrange by bringing dc over here. So I'll get the partial derivative of g with respect to c at constant pressure and temperature is equal to this sum I have in the parentheses here, sum of mu j, nu j. And this quantity we recognize as our definition of delta Rg. Okay, so I have this expression for delta Rg, this sum. I'm going to call this one star star because we're going to use it again here in just a minute. Okay, so now we're going to incorporate activities, which is the reason that we studied this use of activities is the reason we studied it right before we started chapter 6. And for a species J, we saw in section 5F that mu J is mu J standard plus RT ln the activity of species J. And you can find this in my notes on page 107. Okay, so now we're going to sub this expression into the equation that I just labeled star star. So this is what star star looked like. And now I'm going to substitute into this mu j. I'm going to use this for mu j in this expression. Okay, and inside my sum, I have this product. I'm going to go ahead and expand this right here. Okay, so that separates it into two sums. This here is all of the standard state values of mu j times nu j, which doesn't depend on the state. These are just the stoichiometric coefficients. They're independent of the state. So this whole thing is like a standard state. So we're going to call this our standard state for delta Rg. Now, if we look at this term, I can factor out the RT because they don't depend on J. The sum is over J. So RT can come out of the sum. I have nu J ln Aj, which using the property of logs, I can take this nu J and move it up here to be the exponent of Aj. And now I have a sum of logs, a sum of logarithms. So we're going to use another property of logs, which is that the sum let me call it xi, so I don't reuse. So this sum of logs is the same as taking the log of the product of all of these arguments. So this is equal to capital pi, product notation. Capital sigma is summation notation. Capital pi is product notation. So that's going to be, whoops, I need to put this inside the natural log. So let me put natural log product of all of these xi's. Okay, so I can use that right here. And this term becomes the natural log of the product over all j of aj nu j, aj to the nu j. Okay, so let's put all of this together and get a formula for delta Rg. All right, so here's what we ended up with. And so now we're going to compare this to the equation that I called star a while ago, which looked like this. And comparing these two, we see that they're the same. Therefore, this argument here must equal this argument here. So this gives us our definition of Q. We've derived a definition for Q. Q is the product of over all the products and reactants of the activities to the power of the stoichiometric numbers. So that's the definition of Q, the reaction quotient. So remember, these stoichiometric numbers, nu j, are negative for reactants, and they're positive for products. So that means in this formula up here, all the reactants are going to have a negative exponent. All the products will have a positive exponent. So that means that the reactants will all move to the denominator. And so sort of schematically, I could say that Q is the product of Aj to nu j. I'm taking the absolute value now of all the products divided by the product of Aj to the absolute value of nu j for all the reactants. So all the reactants will end up in the denominator, all the products will end up in the numerator. Okay, so to summarize all this, I have equation star, where Q is equal to this, and this formula then gives us delta R G at an arbitrary stage of a reaction. Okay, so let's do a quick example for a chemical equation that looks something like this. So to calculate Q for this reaction, I'm going to need to know the stoichiometric numbers, which I have right here. Right? Negative for these, positive for these. And I'm going to need to know the activities of each. And once I have all those things, I can write out my formula for Q, which is going to be the products, so the activity of C to the power of 1, in this case, is the stoichiometric coefficient, times the activity of D squared, because that's the stoichiometric coefficient in front of D, over the activity of A squared times the activity of B cubed. And if you're wondering what happened to the fact that these stoichiometric numbers should be negative, they are. That's why these numbers appear in the denominator. Okay, so it's that simple to find the reaction quotient for a reaction like this. Now the activities can change with time as the reaction progresses. And so at equilibrium, these activities are going to reach their equilibrium values. And so now, because we have this formal definition of Q, we can now write down a formal definition of K as well. So at equilibrium, the activities reach their equilibrium values, and as we said before, Q is equal to K. That's what we mean by K, is the equilibrium value of Q. So now I can write the formal definition of K, which looks exactly like Q, except all of these values, all these activities, we're using their equilibrium values, the equilibrium values for the activities. All right, so this is our formal definition of K. And K is called the thermodynamic equilibrium constant. So as I mentioned earlier in this video, K is a valuable quantity to know because we know that as a reaction approaches equilibrium, the reaction quotient will approach K. And so we can use this, like in the previous example I mentioned, we could use K to find the ratios of the amount of species that would be present when the reaction reaches its equilibrium. There are many examples of equilibrium constants. So let me list a few. We have this one, the thermodynamic equilibrium constant. We have stability constants. We have formation constants, binding constants, dissociation constants, and others. So maybe some of these you've seen before in a prior class, or maybe you'll see these at some point in the future. These are all examples of equilibrium constants. And I mentioned earlier that this K must be dimensionless. It must not have any units. And we can see that here now in the definition because the activities are dimensionless. And so this is the product of dimensionless numbers raised to a dimensionless power. These are just the stoichiometric numbers. So we see here from the definition that K must have no units. Okay, so I'm going to do some examples of finding the equilibrium constant K. I'm going to save that for the next video. And I'll stop this video here, and I'll see you in the next video.